Welcome back to our class on textile finishing. Let us see what did we do last time when we met. Last time we learned about enzymes and application of these enzymes in textile processing. We are quite sure, we are quite used to using amylase in desizing processes, but we did talk about a finishing process called the biopolishing of cotton fabrics or cellulose based fabrics using cellulase enzymes. Today we will look at finishing of synthetic yarns or fabrics. What does it involve and how do we do it? What type of finishes we may actually be requiring, which are relatively special to synthetic fibers. So, we are quite sure about what are our natural fibers, right? Are we sure? What are the natural fibers? Cotton, wool, silk, jute, all these are natural fibers. Natural fibers have their own functionalities, polarities, because of which various finishing processes that have been handled and used for them. We talk about another set of fibers which are called the manufactured fibers, which do not occur in nature and therefore, we manufacture them. One of the group is called synthetic fibers. A synthetic fiber is a group where the polymer, by now we already know that the fibers are made of polymers. So, in the synthetic fibers, the polymer does not exist in nature at all. So, we take building blocks like monomers and do polymerization and then fiber spinning to make fibers. They are completely synthetic because nothing existed in this polymeric form in nature. So, that became an interesting type of fiber and therefore, it may require something special also. We will talk about it. Then there are other manufactured fibers which are in some way modified fibers, that is, the basic polymer unit exists in nature and you modify, remodel, dissolve, coagulate and then make fibers out of them. And this is therefore in the category, for example, viscose is one of the regenerated fibers made from cellulose basic chain. So, they do not come in the synthetic category, all right. So, synthetics are where the polymer has to be synthesized using monomers. So, some of the synthetic fibers that you are aware of are polyester, nylon, polypropylene, acrylic, Kevlars and so on and so forth. There are so many such polymeric fibers which are synthesized using monomers. So, what about acetate and triacetate? They are not synthetic, they are manufactured because the basic unit, the basic polymeric unit existed in nature, which was cellulose. We modified them to make acetate or a triacetate fiber. What about viscose? We just talked. Viscose is regenerated fiber where cellulose as a base is used and then dissolved in one way or the other and then spin into a fiber. That is the kind of a process that you use, which is called the regenerate. So, these two or the groups of these basically do not come in the category of synthetic fibers. So, in this lecture we are only talking about some of the synthetic fiber or some of the finishes for synthetic fibers, particularly the fibers which are commercially used as textile fibers. We shall not go into the Kevlars and other special fibers which have special role to play. So, the important synthetic fiber that we may refer when we talk about synthetic fiber, which are let us say the textile grade, these are the fibers which you come across almost every day. And so, what kind of a finish do they require? So, before that let us just approximately understand how these fibers are spun. Let us say polyester, we are talking of this fiber which is commercially popular, polyester fiber, PET. So, how is it spun? How? It is melt spun, right. So, you make a polymer and then you melt it, and after making whatever little modifications to the polymer systems which are called, finally you may be having an entity called chips, polymer chips which has to be melted and then spun through extruders and spinning systems. So, you get fibers. That means they are melt spun. What about nylon? 6, there is another one which is also nylon 6,6. How are they spun? They are also melt spun, all right, they are also melt spun. What about polypropylene? This is also melt spun, right. And then we have another fiber which we talked about, polyacrylonitrile or PAN fibers. Are they melt spun generally? Are they melt spun generally? No, they are solution spun. So, it could be dry spinning, or wet spinning. So, these processes could be used to make polyacrylonitrile fibers. Why they are not melt spun? The dipole interactions because of the nitrile group that you have is so strong that when you want to melt it, the main chain also degrades, and there are other processes like cyclization, degradation to yellowness could be seen, and therefore, generally they are going to be dissolved in some suitable solvent and then solution spun and make by either dry spinning or wet spinning. So, we like to understand what type of finishing treatment would be required for synthetic fiber fabrics. Let us say we check it out, we have done a good number of finishing treatments. Let us see how do we go. Would you require a wrinkle resistant finish? Would you want wrinkle resistance, synthetic fabrics? Normally people would say, well, the cotton and the other natural fibers as well as viscose, which is a man-made fiber, would require a lot of attention as far as wrinkle recovery angles are concerned, and so they require a wrinkle resistant finish. People generally believe that synthetic fiber, let us polyester for that matter, would not require so much of wrinkle resistance treatment. But you would want the wrinkle resistance to be good, that is true, but you will be surprised that if you do not give a special treatment to this, then we may not get the same type of wrinkle resistance as you expect. So, actually we require what type of a thing, that we will see. Fire retardancy, are they flammable or not? They are flammable, and therefore, you would require flame retardant treatments. We already know what kind of a treatment that you would like to give. Soil repellency, did we say that some of the synthetic fibers, because of their hydrophobicity, get soiled more, and particularly oil based soils? So, they would require soil repellency, of course, they would require, but we know about this also, we have already studied. Whether they require water repellents, yes, depends on whatever application that you are thinking of. The synthetic fiber fabrics also would require water repellent finish as well. Antimicrobial, this question somebody can ask, would they require antimicrobial? We said they are synthetic, that means these polymers did not exist in nature, and therefore, nature does not have wherewithals to break them down easily. So, are we worried about that the microbes and the bacteria, that is, and a fungus would break down these fibers? We are not worried about that. Okay? What we are worried about is the exudates which get stuck, let us say perspiration, in case of a wound, something else that happens, or blood, or any such thing which can get attached, which may be nice for the bacteria or the microbes, and therefore, you may require antimicrobial treatment for them. We already know what to do. Hydrophilicity. Now, this is something which is interesting. Most of the fibers, most of them are, compared to, let us say, the man-made, other man-made fibers and natural fibers, more hydrophobic. So, in case you require hydrophilicity, we would probably, so they require that also. What else? This is what we said they already require, and what else would be required? What about static charge development? So, do you think some of these synthetic fiber fabrics may have some difficulty in terms of static charge development? If that is true, then we may require anti-static finish. Do you believe that or not? We do. Then we talked about this wrinkle resistant If we do not give this treatment which we call as heat setting, then this wrinkle resistance will be poor. But if we give heat setting, then this wrinkle resistance can improve. So, as such, would you require moth proofing here? No. Any other insect resistant treatment? No. There is interesting thing people sometimes do, which is called de-weighting. De-weighting. De-weighting obviously means removing weight. So, for some nice applications you may require. So, we will actually concentrate on two finishes which are really specific for synthetics which are required. One is the heat setting and the other is anti-static finish. De-weighting, yes, we will just brush upon this at some stage. All other finishes which are generally required for, let us say, waterproofing, yes, you can do waterproofing there as well. Softening, stiffening, all this will be required. Based on the requirement or application, you may require these. Waterproofing, as we said, the synthetic material also are part of the waterproofing treatments. So, they will be required, but they are, we already talked about them. So, the ones which we have not talked about till now, which are specific to these, are going to be heat setting and anti-static. A mention of de-weighting also we will do in the course of next few lectures. So, we start with thermosetting. Okay? We start with thermosetting. So, thermosetting can be done only on thermoplastic materials. There are some material which is called thermosets. The setting can be done there also, but we are not talking about them. We are talking about our textile fiber fabrics, which if they are thermoplastic materials, then we can do this type of setting which we just mentioned, thermomechanical setting or heat setting. So, what is a thermoplastic material? It is a material which would become softened, become pliable, so that you can mold it, crease it, fold it, put it in whichever shape that you want, and that can happen when you raise the temperature. All right. So, that is an important part as far as thermoplastics are concerned. And then after you have done whatever heating you have done, you should cool it down so that it comes to the temperature and becomes more solid, shall we say. This word solidification can confuse. We never heat any material so that it becomes or it comes to a molten state. Of course, we can melt, because we know we have done melt spinning of these material, thermoplastic material. So, if we do take it to a molten state, the shape will be completely lost. For example, if there is a fabric and I take it to its melting temperature, it will be liquid. So, there will be no fabric, right. So, while we will like it to become pliable, we would not like it to get melted, right. So, but from something which is a soft state, they can come to more stabilized state. Okay. So, but of course, their property is there, they can be molten also and they can be solidified also upon cooling, that is of course true. But as far as we are concerned, we may not be interested as a textile person to go after we have made a fabric or a garment or a yarn that we like to melt it again. Normally, obviously, that does become part of finish. So, this process of making it pliable and then cooling it to stabilize, let us say take it to 200 degree centigrade, let us say a polyester fabric, it will have some changes and after that you cool down to let us say room temperature and after that we are happy. For example, something like this could also happen, like you make a crease, right. So, this crease can remain stable for a long period, right. So, that is why, so you heat it like you do ironing, heat it and then obviously let it stay in this position and cool it and after that you find, well, you can see that the crease does not go, all right, or the surface remains as creaseless if you iron it the other way around. So, you make it soft, that is take it to a certain temperature which is high temperature, then cool it down to stabilized. Now, the question is this process reversible? Is this process reversible? This so called process that we are just discussing, heating, cooling, changing the shape, molding, is it reversible? Yes. So, for all thermoplastic materials, this process is reversible. On the other hand, if you are talking about thermoset materials, whatever mold that you make, after that you cannot change that shape, right, even if you reheat. In this case, if you reheat up to the same temperature or little higher temperature, the process will help you to change the shape. So, they are thermoplastic materials. So, now we are talking about fibers. Just for our own refreshing, what are some of the non-thermoplastic fibers? Say cotton, viscose, non-thermoplastic, right? Wool, silk, they are non-thermoplastic fibers. So, the kind of treatment that we are talking about will not be used for such type of material. Okay. So, some of the thermoplastic fibers we already are been talking about it now. So, the synthetic fiber that we talked about, polyester, the nylon, whether it is 6 or nylon 6,6, they are commercial, polypropylene, acrylic, they are thermoplastic fibers. Okay. These are all we said melt spun, this is not melt spun. So, is it thermoplastic? It is thermoplastic at temperature which have to be controlled temperature, some changes obviously can be brought about within this system. So, thermoplastic fibers. So, if somebody says how do you test it is a thermoplastic fiber or not thermoplastic fibers? Have you heard of this? Flame test. So, you take a bundle of fiber near the flame, not in the flame, but near the flame, it shrinks, right, it shrinks. This is one of the tests that you may do to find out whether thermoplastic or not thermoplastic. If you take the acrylic fibers also, they also shrink. All right. So, they will be thermoplastic, but cannot be easily melted. That is a separate story, but they can be molded. The creases can be put. Some of these things can be done at appropriate temperatures. So, this flame test that we talked about, it said fibers shrink. Why do you think the synthetic fibers shrink when you take it near the flame? Why? We did talk about relaxations. So, this is a relaxation process. What do you mean by that? The fibers, when they are made, they are drawn. That means oriented along the fiber axis. Is true? We draw them, spin and draw. So, what happens? The molecules are stretched in the direction of the fiber axis. So, and then you cool them. So, this is the thermoplastic behavior, right? You just draw them and then cool them. So, let us say at a higher temperature you have drawn them and then cooled them. The molecules they remain in a more oriented form. They cannot go back to their random state. So, molecules do not like it. That means there is some stress already been stored by this process, right. So, whenever they get an opportunity, like you raise the temperature again, whenever there is kinetic energy available, the motion and the molecule sets in, and they would like, if possible, to go back to little more random state. That means disoriented state. Not completely disoriented. If you melt it, obviously it will be a completely disoriented state, but if you just heat and give an opportunity, that means do not put tension, the molecules would try to go to some best position that they like. So, that is what is the relaxation process, and therefore, the whole fiber appears to be now reducing in length, that is called the shrinkage. So, that is what happens. So, that is the thermoset material responding to heat. You heard about this famous equation? This is a very important equation, which is thermodynamic equation for various types of things that happen in the world, even in the so called domain of synthetic fibers, which do respond to heat, for example. So, what this says that if a material is in one state, whichever state it is, it wants to go to the other state, it will happen spontaneously. For example, if you bend something, release the bending forces, it becomes straight, because by going to this, it is releasing energy. So, what it says is, if this change in the free energy is negative, that is delta G is negative, then whatever change we are talking about will be feasible, will be automatic, thermodynamically feasible process. What it means therefore is, there is this term which is related to, let us say, internal energy. If this is negative, it is a good idea, then it is helping the state. There is another term which is here, which is called the entropy, which represents the disorientation. So, entropy of the universe always increases, that means delta S is always going to be positive. More and more randomness. If more and more randomness takes place, more and more disorientation takes place because of our action, like taking material to a little higher state, a higher temperature, right, by heating, then this is going to be positive. So, if delta S is positive, this term also is negative. If both the terms are negative, then the delta G is negative. Now, it depends on what is happening. If one of them is positive, the other is negative, which is more negative, which is more positive. Finally, delta G, if it is negative, then this process will be spontaneous. Now, in our case, what does it represent? A delta E, for example, in the case of fibers and this heat setting or thermomechanical setting, could represent crystallization process. Do you know the crystallization? Is it an exothermic process or an endothermic process? Crystallization. The crystallization is an exothermic process. So, that gives a negative. So, whenever any material after heating goes through crystallization process, will be going towards a stable state. Okay? That means delta G will be negative. And as we already mentioned, this is like entropy increase, that means disorientation. So, whenever there is a chance, so fiber will shrink. If given a chance, it will like to crystallize. If both the things happen, then you will go to a state which is stable. Purpose of heat setting is to make state stable. If you form a crease, it should remain like a crease. If you you make a surface absolutely smooth, it should remain smooth. That is what the thermomechanical setting would do for you. So, setting is by release of energy. Okay. So, what does it mean by release of energy? If we just understood the delta G, so let us say we have a curve which has got some energy state, let us say state 1, we have not done anything, let us say a fabric as it is. After that, it was stable because it was not changing its position. So, it was stable, but you let us say put a crease and then start heating. As you start heating, crystallization can start, disorientation can start, and it can go to a state which has got a lower energy, let us say a state 2, and then you cool it. Now, the tendency of this fabric which has attained this state to go to this state will be very low, because you have to go higher the energy ladder, which the fiber may not like. So, what you are doing is creating a barrier, energy barrier. So, if this has to go from here to here, it can go, which we will call it setting, from a higher state of energy to a lower state of energy, which will finally make delta G negative. This is what will be happening. And why will it happen? Either it will be crystallizing or it will be disorienting. Other thing that we had talked about for setting, which we have done earlier, is setting everything in position, which means cross linking, which we have done for the non thermoplastic material. Okay. So, the non-thermoplastic material can be cross-linked, like we have done DMDH-EU on cotton for that matter, right. So, but for synthetic fiber it is the release of energy by thermomechanical means. So, this is thermomechanical setting, sometimes it is also called heat setting, and how the setting takes place is by release of energy. Release of energy means it may be crystallizing as well as getting disoriented based on how much tension and what temperatures are kept. Now, what temperature should be used for doing this process? If you draw a plot of a temperature versus let us say rate of crystallization. Right. This curve is something like this. That is, at as the temperature would increase, the rate of crystallization, crystallization means molecules coming together making a nice beautiful crystal that every atom is in a certain specific position, etc., will increase. So, these synthetic fibers do crystallize and rate of crystallization will increase, but after a certain temperature it will start decreasing, because the kinetic energy will be so much that whatever little opportunity that they get to come together, they also have equal opportunity to stay away, because you are giving lot of energy. At some stage we may have a situation where the rate is almost getting 0, right, which may be melting, temperature for melting. This temperature, if we call it T star, is the temperature where rate of crystallization is maximum. All right. So, theoretically we would be, if we go somewhere at the, if this is rate of crystallization K star, if we go to somewhere around half the width, which is K star by 2, and approximately this temperature is maybe a softening temperature. We may not go even to this point, because there may be some adhesion, fusing of fibers. There is no point going in up to this temperature, there is no point in going up to this temperature. Somewhere around this temperature is the one, there will be an optimum setting temperature where the rate of crystallization will be high. So, you go up to this temperature, hold it for certain time and then cool it, so that it comes back to room temperature. So, new structure, new morphological structure will be stabilized, all right, and this will happen thermodynamically if you have gone beyond a certain temperatures. What will happen is reduction in free energy, means it will crystallize, and of course, at the same time molecules may get disoriented also. So, we have seen the energy curve. The energy curve is that you happen to be state 1 in 1 and then you come to state 2, all right. If you come from state 1 to state 2, it will be called, let us say, a permanent set. Nothing is permanent as such, but if you somehow are already in this state and you want to go to this state, let us say there was a crease state which were quite stable, now you want to go to another state. Well, if that is what can happen, then you can change. So, we did say that from any state to any state it can go. This setting will be reversible, all right. And so, you can have crease. If you do not want crease next time, you go to the same temperature, do the reversal, it can go to the other state. So, from one state to another state can go, and that is what we can call as an energy state. Okay. But if suppose you wish that you do not want to increase the temperature at all, automatically this will come to this state. It may not happen, because even a fully drawn yarn which has not been heat set is also partially crystallized. Textile materials are semi crystalline materials, is that right? Okay. So, during this setting process, both crystallization and disorientation will take place, all right, and both are thermodynamically favorable. The energy will go down in both these cases. What can be set? Well, we can do the setting of yarn, like heat setting of yarn can be done, no problem on that. So, drawing and heat setting of the yarn can be done. If you just draw, it will shrink more tendency. If you draw and heat set, which means you are stabilizing. So, process of heat setting basically makes the system more stable by bringing the energy of the whole system down, all right. So, stable system. Of course, we can do fabric, that is the finishing. For example, any fabric you can iron, you can pass it through a stenter at a different temperatures, and so you would be able to finish the fabrics. You can crease, make pleats, all that can be stabilized by thermomechanical process. So, what temperatures? Some guidelines we can get it from that rate of crystallization curve, and in general, if we have polyester, for example, fiber is polyester, polyethylene terephthalate, from about 200 to 210 degrees centigrade could be a heat setting process temperature. Nylon 6 may be around 170 to 180, all right, degrees centigrade. If you have nylon 6, which obviously is a different fiber, nylon 66, it can also be from 200 to 210. You can set it. If you happen to be handling polypropylene, then maybe 125 to 130 degrees centigrade is what may be required now. It could be 30 seconds to 1 minute, depends on what kind of thickness of the fabric is there. So, you pass it through, let us say a stenter, everything will be done nicely. Do we allow for shrinkage to take place during this process? Of course. To make it more stable, it is better to allow it to shrink a bit. So, dimension control can be done. How much shrinkage processor would like to do, that you decide 5%, 7% shrinkage in any of the direction, let us say in the warp direction, you allow that to happen, and then finally the fabric will be more stable, okay, as far as that is concerned. So, what is the major effect of heat setting? Major effect is dimensional stability. The dimensional stability is coming because you are taking, by this thermomechanical process, the whole system to a lower energy state. And how does it happen? By increase in crystallinity and possibly decrease in orientation as well. All of them, they are not exclusive in the sense that only one will happen, the other will not happen, both can happen, that is one important. So, dimensional stability occurs because of this. So, it will not shrink. When you do hot water shrinkage measurements, it will not shrink to any significant effect. Like you do laundering in a higher temperature, the garments will not shrink. This is what will there. If they have been set in a flat state, they will not crease also. So, that is also very important thing as far as we are concerned. Will it affect dyeability? Let us say we talk about polyester. Which dye it is dyed from? Disperse. Okay. Disperse dye, it is dyed from disperse dye, is that right? Good. Now, the dispersed dye goes into the spaces that are available, this is when the dyeing is done, let us say higher temperature, there is molecular mobility, some space between the molecules is created and then dye diffuses inside, dispersed dye. It is not dependent on any functional group. So, what is dependent on? It is dependent on the morphology. How much is the crystalline region, what type of crystals are there, what is the space available, because the dye is going to go to the amorphous portion. Remember we said the textile fibers are semi-crystalline. So, there is crystalline portion which gives the dimensional stability, but the unoriented or amorphous, maybe oriented amorphous regions which are non-crystalline will allow dye diffusion to take place, it is good for us. So, if you want to measure the dye uptake versus let us say heat setting temperature, remember we are not talking about dispersed dye, let us say any synthetic fiber like polyester. So, what is happening by heat setting? We said crystallization will take place. So, as you increase the temperature, more and more crystallization will take place, true. So, what will happen to dye uptake? Will it increase by heat setting temperature or decrease? So, we expect it to decrease. If more and more crystallization takes place, the percentage crystallinity in a fiber increases, then we can expect the dye uptake to go down compared to without heat set, let us say a fabric or a yarn. After that what happens? Well, one notices that the uptake after some time then start increasing. Does it mean the material is becoming less crystalline? Have we gone to a temperature which is much beyond the temperature of heat setting? No, 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 no. Even without that, what people have found is that as we increase the temperature, the crystallinity increases, maybe not to same rate, because the space may not be there enough. A large number of molecular segments have already crystallized, the one which are non-crystalline portions of the molecule. How do they come close? Because they are being hindered by the already crystalline portion, because invariably you may have been told that the molecules fold on each other during this crystallization process, and then they pass on and go to the next crystallite region. But during this heat setting process, other than crystallization, as we move further, other thing which happens is smaller crystals can merge into a larger crystal, and if that happens, then even at the same crystallinity level, the space available for dye to diffuse starts increasing. What people now term this as a amorphous volume available per crystal. This increases, and therefore, dye can go further, and that is how we see this type of a behavior, all right. Very interesting behavior in synthetic, particularly for the dyes which are more dependent on the morphology, right, the internal crystalline morphology. It has an effect. Mechanical properties, of course, it can affect if the disorientation takes place, maybe the tenacities can go down, but if you keep on stretching and then heat setting, the tenacity can increase. So, mechanical properties would depend more on the orientation. If more orientation takes place along the direction of the axis that we are interested, then the mechanical properties can increase. If more relaxation is allowed, the mechanical properties can go down a bit, that means tensile strength can go down a bit, but that is okay, that is not going to affect anything too much. So, what have we learned? We have learned that the thermoplastic fibers shrink, and that is akin to a relaxation process, where the molecule which was already stressed quite a lot now shrinks to relax, which is thermodynamically a feasible process, where as we say the entropy increases. It also involves development of crystalline structures, which in some sense is responsible for reducing the internal energy, which is also good, a thermodynamic process to make systems more stable. And this morphology which develops during this process of heat setting can affect the diability in one way or the other. If somebody asks a question at what temperatures you should be dyeing, for example, you got a very interesting temperature curve. A curve like this, what should be the nice temperature as far as the dyer is concerned? A dyer would prefer a temperature range from here to here, where if there is a variation in temperature, the change in the dye uptake will be least. If you start dyeing here, then a small change in temperature can change the dye uptake more, and you can have non-uniformity in the dye uptake, and so that may not be a good idea. So, that is one simple comment. Next time when we meet, we shall talk about the other important property or finishing treatment, which is antistatic, which is specifically required for the synthetic fiber fabrics. See you next time. Enjoy till then.